Hello, everyone, and welcome to our first lecture online for POL 551. Here, I'm going to cover the topics of bias and efficiency. And to get started, we're going to pose the same question that I pose at the start of every single one of our classes. And that is, how much does a relationship that exists in our data reflect a relationship that exists in the real world? So if we're seeing a bivariate regression, a beta coefficient, or some Pearson's R correlation statistic, does that reflect a real relationship or a real pattern between two political phenomena? Or is this something that simply occurred due to chance? And in the vein of answering this question, but prior to our spring break, we covered the logic of regression, specifically how much a 1-unit change in our independent variable affects the amount of change in our dependent variable. We then talked about how to specifically interpret these beta 0 and beta 1 coefficients. We talked about finding the goodness of fit of our regression models using the R-squared statistic. And then we actually went through an entire exercise of making statistical inferences about beta 0 and beta 1 in order to support or disprove our hypothesis. What we're going to do in this lecture is cover the properties of ordinary least squares regressions, OLS. Specifically, we're going to talk about bias and efficiency. So as a little bit of a refresher, after the couple weeks off, here is our linear regression model. And here we are trying to explain our dependent variable y with the following equation. First, we're going to be explaining our dependent variable y using a beta 0 y-intercept coefficient. This represents the value of our dependent variable when our independent variable is 0. Added on to this y-intercept, we are going to have our beta 1 coefficient. This is going to be our slope coefficient that represents the change in our dependent variable for each individual 1-unit increase in our independent variable x. We multiply that slope coefficient by our independent variable x. And then the final piece here is our residual error term, random error term. And the reason we have this is because our dependent variable y is stochastic. We can't fully explain it with observable data. It also contains an element of chance. And it's this random error term or residual that captures this stochastic element. Okay, so what are our properties of ordinary least squares regression? Well, the main properties that we're going to talk about are based upon the Gauss-Markov theorem, whose assumptions we are going to cover in more than plenty of detail throughout the remainder of the semester. But as our friend Tobias Fuke here is showing us, while he's dressed up for the Blue Man Group, is that ordinary least squares regression is blue. OLS is the best linear unbiased estimator. So let's unpack what each of these words mean. And I'll start with the E for estimator. This is the easiest one to understand because essentially what this OLS equation is doing is estimating our dependent variable y. So OLS is simply a method of estimating political outcomes or our outcome variable, our y. The next term that we've already heard before is L for linear. We've talked about this ever since correlation, where we have a scatter plot of data points with a line that best draws through them. And here with this term linear, it's the notion that as x increases, y is going to either increase or decrease by the exact same rate across all units of x. So those are two we've heard before. Now that leaves us with B for best and U for unbiased. And here, the best way to start understanding what best and unbiased means is to really start by thinking about the concepts of bias and efficiency. So to do this, I'm going to switch from our PowerPoint to a whiteboard. Now imagine I have some data about students performing in an undergrad methods class. And I'm interested in the relationship between their attendance, which I'll call my X's, and the grade that they get on their midterm, which is their Y. And imagine I have observations for 15 students. So I have someone that has 1 absence, 5 absences, 6 absences, 2, 0, 0, 1, 2, 3, 7, 4, 1, 1, 0, 2. Yikes. And then for my Y's, for their midterm grades, I have a 100, 82, 76, 91, 96, 100, 93, so on, so on, so on, so on. I have a set of values for each of these in a column. Now, imagine I put these values into Stata, I run my linear regression, I do my Y, my reg YX, and I get a beta 1 of the relationship between attendance, or number of absences rather, and midterm grade, and that beta 1 is negative 2.625. Okay, and let's see if I can clear. Let's see, eraser. Let's see if we can clear out some of this at the bottom. Nice. Cool. We're going to clear out some of this at the bottom here. And let's think about this N of 15 that we observed. Now imagine here on my x-axis, I have my beta 1 coefficient. And here in this sample of 15, my beta 1 coefficient is a negative 2.625. Now here my y-axis is going to be the probability of observing that beta coefficient. And I observe it once in a sample of 15, but what I can also do is draw infinite numbers of samples of 15 and plot their various beta 1 coefficients for the relationship between absenteeism and midterm grades. And I could keep doing this into infinity until I get this distribution. And what we ultimately have here in the distribution I'm drawing out is a probability distribution for the sample statistic of beta 1. And as I mentioned at the start of this semester, any type of probability distribution of a test statistic is called a sampling distribution. So here we have our sampling distribution of beta 1. And with infinite sampling, what we know is that this distribution is going to be normally distributed. And it's going to have a mean. What bias and the concept of bias, unbiasedness is that this mean of our, the mean of our sampling distribution. So our expected value, oh my gosh, where did that go? Here we are, we're back to that. So the mean of the sampling distribution of beta 1, and the reason I'm drawing the little hat here is it's estimated. So we have a sample, we're running our regression, we're getting our beta 1 statistic. So that's our estimated beta hat. So this expected value or mean of beta hat is going to be equal to the true beta coefficient in the real world or in our full population. So in our one sample, our beta 1 was negative 2.625. And we could do another sample of 15 students and their beta 1 could be negative 2.35. And another sample could be negative 3.1, and so on and so forth. What this concept of bias tells us is that in infinite sampling, the average value of this sampling distribution, or the average value of our beta 1, is going to be equal to the true population parameter of beta 1. So what this means in practice, that we could say on average, our beta 1 coefficient is going to be the same as the true beta in the population. Okay? So keep in mind, we only have small samples of data, but we can say that on average, the beta coefficient we observe for this small sample of data will be equal to the true population parameter. That is unbiasedness. That is the property of OLS. So let me go back to here from the beginning. So if I go here, I'm talking about bias and unbiasedness. An unbiased estimate is one whose estimated beta is equal to the true population parameter. Now, I have a couple different terminologies here. I have this theta symbol here. I believe a couple of your textbooks have that, but theta and beta, exactly the same thing. So when I'm saying estimated theta hat is equal to theta, or estimated beta hat is equal to beta, they both say the same things. When you have an unbiased estimate, its average value in infinite sampling is going to be equal to the true population parameter. So that is unbiasedness. In contrast, what bias is that distance or difference between what we observe in any one sample and the true population parameter. So when we have unbiasedness, this does not guarantee that any one particular estimate of beta will be equal to the true population parameter. It's just saying that on average, our estimate will be accurate. This is why as you read articles or textbooks about regression coefficients, and it talks about this relationship between X and Y, it will always say on average, X affects Y, or on average, we'll see a relationship between X and Y. It's accounting for this notion of bias, that on average, the beta coefficients we calculate will be the same as the true population parameter. So this is the U in blue, that when we use OLS, that beta coefficient that we get is going to, on average, be the same as the true population parameter of beta. Okay? Now, when that is not the case, so when our beta hat is, or the expected value of beta hat is not equal to the true population of beta, that is bias. So if we're looking here, imagine this is the true sampling distribution in the population that has its true beta coefficient. This might be the distribution from the biased estimate. So it's the difference in means of sampling distributions between the distribution that has the true population parameter and the one that on average is off. Now you might be asking yourself, why would this occur? Why would we have bias in these sampling distributions? And as we'll talk about later in the semester, there's certain OLS assumptions about including certain variables or omitting certain variables that will induce bias. A lot of times this has to do with systematic errors in our sample selection. So if we're looking at the relationship between absenteeism and midterm grades, if we already have a bunch of student geniuses who don't need to come to class or not, we might not find a relationship. And that's just because of a weird sample we picked. So usually if we see bias, it's because of these kinds of systematic errors in our own research collections. Anywhere from sampling biases, biases of case selection, all the way through the types of variables we choose to include or not include in our regression models, okay? So that's bias. Next, let's talk about efficiency. And to do this, I'm gonna see if I can, oops. No, we can discard those. Let's go back here to my little whiteboard sampling distribution. So we talked about the sampling distribution of beta hat. Now, this sampling distribution, like all sampling distributions, in addition to having a mean, also has a standard error or standard deviation. So here, standard errors are the standard deviation of a sampling distribution. So standard error is the standard deviation of sampling distribution. So what we have learned when we talked about the central limit theorem is that the larger our sample gets, the smaller our standard deviation. Same is true when we think about standard errors in sampling distributions. So the larger our samples, the smaller our standard errors. And what a standard error means is basically a quantitative measure of how wrong we are from one particular beta coefficient and this expected value of the whole sampling distribution. So keep in mind, when we run a regression in Stata, we're only using one sample and one snapshot in time. So our one snapshot in time might come down from here, where maybe it's -3, or maybe it's the one that I calculated that's -2.625. Or maybe it's another one up here that's a -1.5. Each time we get a sample, run a regression, get a beta coefficient, we'll get a different outcome. And the difference or distance between each one of those beta coefficients and its true mean, which is the true population parameter, is the amount of error we have. It's just how far off we are. So in a world, we're going to clear this all out. So in a world, say we have two sampling distributions of our beta hat. Okay. Let's do some erasers. Clean up. Go back to draw. So here's one, and here is two. Okay. So there we are. So in our first sampling distribution of beta hat, it has longer, wider tails. Our second sampling distribution of beta hat is narrower and taller. Let's say each of them have the same mean. They each are unbiased. They have an expected value that is equal to the true population parameter. Now keep in mind, we can only pull data from only one observation. if we're in a world with this sampling distribution with really wide tails, yeah, we could pull a beta coefficient from the middle there, or down there, or there. We can also likely pull it from out in the tails. With this taller, narrower distribution, though, we're more likely to pull our beta coefficients from any individual sample from closer here towards the mean. So when we have these sampling distributions of beta hat that have smaller standard errors, they're known as being more efficient, because the likelihood of any one single beta coefficient drawn from that sample being close to the true population parameter is higher than, say, in this wider, fatter distribution where you can pull beta coefficients from way off in the tails. Okay, so let's go back to our slides here. So when I talk about efficiency, I am talking about an estimation of beta that has the smallest variance possible, or the sampling distribution of beta hat that has the smallest standard error. So in an efficient estimator, the sampling distribution of beta hat, or depending on which textbook you read, beta hat, will be tall and narrow. So the tall, narrow distribution I drew, that is the efficient distribution. The one that was wider and fatter is the more inefficient distribution. The goal of using an efficient estimator gives us more confidence that our individual estimate of beta hat, so that regression coefficient that we get out of our data output, is going to be closer to the true beta in the population. It's basically increasing our confidence that any single beta coefficient is equal to the true beta in our population. Now, the fact that I even made this statement implies that we're dealing with two unbiased sampling distributions. Okay? So a much prettier figure of what I drew out on my whiteboard. We have the larger, fatter tails, the inefficient distribution, and then the taller, skinnier, narrow distribution, which is the more efficient. So in OLS, when I say it is blue and I say B is best, the best distribution is the one with the smallest standard errors. So as the standard errors get smaller, this width of the distribution shrinks. So when you have the best, you are actually going to have a sampling distribution that converges right here onto the estimate of beta hat in the true population. With the most efficient, it's just going to be right here. Okay? Cool. So that's efficiency. Now, you might be asking yourself, well, what's better, what's worse? You know, we have bias and we have efficiency. Bias is talking about on average being right. Efficiency is talking about how close we are in any one single draw from the population. And there's a question of what's worse? Having a slightly biased estimator that's really, really efficient, or having an unbiased estimator that is inefficient. So in an ideal world, it'd be great to only look at unbiased estimators and pick the best one. But maybe, maybe not. And actually, no, we should. Sorry. We should only look at unbiased estimators when trying to pick the best one. So here, in order to do this, we have a calculation known as mean square error. Now, you don't have to memorize this. I'm not going to ever ask you to write it out in a homework or other assignment, but this is for your information. What mean squared error gets at is a trade-off between low bias and low efficiency. So what we have here is the difference between our beta hat, so our estimated beta, and the true beta coefficient, so that gets at our bias component. And then this squared component here gets at the squared error, or that kind of variance. So basically, an unbiased estimator, the MSE is equal to its variance. So here's what I'm talking about with this trade-off. So obviously, this is our more efficient distribution. It has the taller, narrower peak compared to the wider, flatter distribution. However, the wider, flatter distribution is the one that's unbiased. On average, its estimates are equal to the true population. So this little area here, that's our bias. However, like I said, we only get one draw from a population. So in this unbiased distribution, we could get a draw from out in the tails, or we could get draws that are right around the true population parameter. In our more efficient but biased estimator, yeah, on average, we're going to be wrong, but in any single draw from the population, in any single beta coefficient we select, we're on average, or not on average, on any single draw that we have, we're probably going to be closer to the true beta. So this is where mean squared error comes in. It looks at that trade-off. It looks to see how much bias you have in between your estimators, and how much of that can kind of be accounted for by having more efficiency. Again, you're never going to have to calculate this. You're never going to have to actually look at sampling distributions and make this judgment call, because again, sampling distributions are theoretical. You're never going to actually see an infinite number of samples calculating beta coefficients. This is just knowing what these principles are and knowing what they mean in terms of OLS. Okay. With that, I'm going to wrap up this lecture. And if you have any questions, let's see, just go to the discussion board, start a thread, say bias and efficiency discussion or lecture. Ask any questions you have about bias and efficiency, and we can go with the conversation from there. All right, take care, and we will talk soon.